Section 3.1 covers how to solve systems of equations using 3 different methods, with this first set of notes focused on solving them by graphing. First, let's define what a system of equations is. It's when we have 2 or more equations that are paired together. When I say they're paired together, it means that the variables are the same throughout the system. So in other words, if x equals 3 in the first equation, it's going to also equal 3 in the second equation. Same thing with the y variable and any other variables that exist in the system. A system can have 0, 1, or infinite solutions, and since we're focused on solving these by graphing right now, this is what they would look like. So a system with no solutions is just going to have parallel lines that never intersect. When we have one solution, we have lines that intersect at one point. So there's one point where x and y, an xy coordinate point falls on both of those lines. And then the third situation is when we have lines that are actually right on top of each other. It's really the same line. So there's an infinite number of xy coordinate points that lie on both these lines. We can define these systems as consistent or inconsistent. Okay, a consistent system is going to have at least one solution. So when we look at these, a system with no solutions is inconsistent. Since these two have answers, they're consistent. Once we label them as consistent, we can also label them as dependent or independent. Independent is when they have one solution. These lines are running independently of each other. Dependent is when we have infinite solutions. These lines track with each other, they're dependent on each other. So if we want to solve a system by graphing, we're just going to graph both of our lines here, and we're going to find out where or what type of system from the previous slide we have. So let's look at this top one up here. All right, so we have y equals 2x minus 1. Y-intercept is -1, slope up to and over 1. So graph it out. It's not a perfect line there, but we'll run with it. And then the second one, -x plus 2. So it starts up 2, and then it's going down 1 over 1. Okay, so I'm just graphing these in slope-intercept form. All right, so when we graph these, we can see that they're intersecting. Looks like they're intersecting there at 0.11. All right, so number of solutions. It's intersecting lines, so there's one solution. Consistent or inconsistent, since they intersect each other, this is a consistent system. Okay, and then this next one we only do for consistent systems. So dependent or independent, these lines are running independent of each other. One's going one way, the other's going the other way, independent. What is the solution? It's the point of intersection, so 1, 1. Here we have 2 lines that are written in different forms. So this top one is in point slope form. When we work in point slope form, we want to take the opposite of these 2 numbers. So we're going to start off with the starting point, -2, -1. Opposite of the x, opposite of the y. So -2, -1 is here. Okay, and then our slope, which is this line right here, 1/2 up 1 over 2. Okay, same thing as this last one, just graph this first line. Okay, looks like that. All right, on the bottom we have slope-intercept form. Y-intercept is 0, so it starts at 0, 0, and then it's going up 1 over 2. All right, so we can see that these are actually the same line. They're running right on top of each other. So number of solutions for this would be infinite. Okay, there's infinite number of points that satisfy both equations. Right? There are solutions to this. There's an infinite number of solutions, so this is consistent, but this time we have dependent lines. These are not running independently. Independent meaning they go in different directions. They're dependent. They're moving the same amount each time. So what's the solution? Okay, typically we would just write all real numbers, which is this fancy looking R with 2 lines on it. Now, when we have a system, we can usually answer what type of system it is just by looking at the slopes. So if we look at these slopes here, we can see that they're different. It's impossible for these to be the same line. It's impossible for them to be parallel because parallel lines would have the same slope. So we know that the number of solutions is going to be 1. These are going to be intersecting lines. All right, let's graph this top one. Slope-intercept form, it starts at a y-intercept of -2, and it's going down 3 over 1. All right. This next one starts at +1, and it's going up 2 over 1 for the slope. All right, now the difference with this one compared to the last one is that they're not intersecting on an exact point here. We're kind of in the middle of 2 points. So in a situation like this, we're just going to estimate it. So we have a point of intersection that's about here. Okay, and as long as we're in the area, we are just going to kind of guess what it is. So when we look at this, again, this is consistent because these lines intersect. The lines are moving independently, meaning that they move in different directions. Now, for what is the solution? It's definitely to the left of the origin, so we want a negative x coordinate. So let's say negative 1/2. All right, and then for the y coordinate, it looks like it's pretty much on the y-axis, so negative 1/2, 0. All right, would be a good guess. Anything around there would be acceptable. So all those rules are for linear systems. They can have 0, 1, or infinite solutions. In this case, we have a system that's nonlinear. It's nonlinear because this top equation here is an absolute value graph, meaning it's going to make a V shape. So let's graph this one first. Okay, we just want opposite for the x, same for the y, negative 2, negative 2. Okay, so we're down here for the vertex of this V. Once we have that vertex, we're going to look at the slope, okay, which is in front of the absolute value. It's really just 1 over 1, up 1 over 1. Okay, so we have that side, and then on the other side, we just have the opposite slope. So really down 1 over 1. Okay, it's going downhill, or we could look at it as viewed from going up 1 over 1 in the opposite direction. So that's our first graph. Second graph is in point slope form, opposite of both for point slope form, negative 1, negative 1. So we're here, and then slope is down 1 over 4. All right, looks like that. Okay, so since this is nonlinear, we're going to actually have 2 solutions for this. Okay, we can see that it's intersecting the graph 2 times. We don't have to deal with consistent, inconsistent, dependent, independent, because those are only for linear systems. As for what our solutions are, it looks like, well, we have that one intersection at negative 1, where they started. And then we have a second one, which is in the middle again. And it's hard to see because these lines are so long, but we would estimate this. Looks like it's at about negative 3 for the x. So we have the first one at negative 1, second one around negative 3, and then it looks like it's a little below that x-axis there, so maybe negative 1/2 for the y. Okay, again, anything in that general area is okay for an answer when we're solving by graphing.